welcome to this. So in this session, we are going to prove that the set of all m by m matrices of a field F is a vector space with respect to usual matrix addition and scalar multiplication. So proof. So let A with the matrix A11, A12 up to A1n, A21, A22 up to A2n, and then AM1, AM2 up to AM n, and let matrix B be given by B11, B12 up to B1n, and then B21, B22 up to B2n, and then BM1, BM2 up to BMN. Let matrix C be given by C11, C12 up to C1n, and then C21, C22 up to C2n, CM1, CM2 up to CMN, and then where A, B, and C are matrices of order m by n, and let alpha and beta be two scalars in the field F. So then we have to show that all the 10 axioms of a vector space are satisfied for these matrices. So first property is closure with respect to addition. So if we take A plus B, we'll have A11, A12 up to A1n, A21, A22 up to A2n, AM1, AM2 up to AMN, plus B is B11, B12 up to B1n, B21, B22 all the way up to B2n, and then BM1, BM2 up to BMN. This sum will be, remember when we're adding matrices, we add corresponding elements. So the sum here will be A11 is added to B11, A12 is added to B12, A1n is added to B1n, A21 is added to B21, A22 is added to B22, A2n is added to B2n, and then AM1 is added to BM1, AM2 is added to BM2, all the way up to AMN is added to BMN. And you see this resulting sum is still a matrix of order m by n. So this is still an element in this set m, f, m by n. So therefore, closure with respect to addition holds on this set f m by n. Number 2, commutativity. Now for commutativity, we check that A plus B is equals to B plus A. So A plus B, from what we have gotten in A above, is A11 plus B11, A21, A12 plus B12, all the way up to A1n plus B1n, A21 plus B21, A22 plus B22, all the way up to A2n plus B2n. And then we have AM1 plus BM1, AM2 plus BM2, and then AMN plus BMN. I remember AIJs and BIJs, all these are real numbers. So because real numbers are commutative, or we can commute real numbers, then this sum can be written as B11 plus A11, B12 plus A12, B1n plus A1n, B21 plus A21, B22 plus A22, up to B2n plus A2n, and then this one will be BM1 plus AM1, BM2 plus AM2, all the way up to BMN plus AMN. So what is making us to move from this step to this step is because since addition is commutative, in the field F. Now this sum in this result must have come from the vector starting with Bij's and then added to vector starting with Aij, so matrix. So that can be written as B11, B12, up to B1n, B21, B22, up to B2n, BM1, BM2, up to BMN, and then plus A11, A12, up to A1n, then A21, A22, up to A2n, AM1, AM2, up to AMN. And this is the definition of matrix B. This is the definition of matrix A. Remember, we came from A plus B. So A plus B is ending up to be B plus A. So we say commutativity holds. Commutativity holds on this set of M by N matrices. Number 3, we prove associativity. So associativity will show that A plus B and then plus C is given by A plus B plus C. So I have to show this. Now, if you start with A plus B plus C, then we have A11 plus B11, A12 plus B12, up to A1n plus B1n, and then A21 plus B21, A22 plus B22, A2n plus B2n, all the way up to AM1 plus BM1, AM2 plus BM2, up to AMN plus BMN. And then we add to the matrix C. C is given by C11, C12, up to C1n, and then C21, C22, up to C2n, all the way up to CM1, CM2, up to CMN. Now, these are two matrices, so we add corresponding elements. So that will be A11 plus B11. You add it to C11, A12 plus B12 is added to C12, all the way up to A1n plus B1n is added to C1n, and then A21 plus B21 is added to C21, A22 plus B22 plus C22, and then all the way up to A2n plus B2n, you add it to C2n, all the way up to AM1, AM2, ABM1, you add to CM1, and then here we have AM2 plus BM2 plus CM2, all the way up to AMN plus BMN plus CMN. So this is the sum. And since Aij's, Bij's, andCij's are real numbers, or are the elements in the field F, then they obey associativity law. Therefore, this can be written as A11 plus, now I change the location of the brackets, B11 plus C11, A12 plus B12 plus C12, all the way up to A1n plus B1n plus C1n. And then I have A21 plus into B21 plus C21, A22 into B22 plus C22, all the way up to A2n plus B2n plus C2n, and then all the way up to AM1 plus BM1 plus CM1, AM2 plus BM2 plus CM2, all the way up to AMN 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 plus into BMN plus CMN. So this is what I have. So reason as to why we are moving from the previous step to this step is because since Aij, Bijs, Cijs are elements in F, and associativity with respect to addition holds in F. So that is what is making us to change the location of the brackets. Now this one shows that we had matrix with Aijs added to matrix of some Bijs and Cijs. So the next step will be A11, A12 up to A1n, A21, A22 up to A2n, all the way up to AM1, AM2 up to AMN, plus the sum of B11 plus C11, B12 plus C12, all the way up to B1n plus C1n, B21 plus C21, B22 plus C22, all the way up to B2n plus C2n, and then you have BM1 plus CM1, BM2 plus CM2, all the way up to BMN plus CMN. This tells us that we have A11, A12 up to A1N, A21, A22 up to A2N, all the way up to AM1, AM2 up to AMN, added to. For us to have gotten this sum, we must have a vector or a matrix with Bijs added to matrix with Cijs. So this will be B11, B12 up to B1n, B21, B22 up to B2n, and then BM1, BM2 up to the way BMN, plus C11, C12 up to C1n, C21, C22 up to C2n, all the way up to CM1, CM2 up to CMN. And you see this is the definition of matrix A into brackets, this matrix B in plus matrix C. And remember, we started from saying into brackets A plus B, then plus C. So this side was into A plus B, and then plus C. So you see, we have successfully shown that associativity holds. So therefore, associativity with respect to addition holds on this set F M cross N. And then number 4, additive inverse, additive identity. So we show that if we have a matrix denoted by this one with this element, zeros everywhere, then when we add it to the matrix A, then we'll have A11, A12, up to A1n, A21, A22 up to A2n, AM1, AM2 up to AMN. When you add it to a matrix whose elements are all zeros, and for the m by n, and then we have this. Now, so because this matrix and this matrix have the same order, then we can always get the sum. So this would be the same as A11 plus 0, A12 plus 0, all the way up to A1n plus 0, A21 plus 0, A22 plus 0, all the way up to A2n plus 0. And then AM1 plus 0, AM2 plus 0, all the way up to AMN plus 0. Now, 0 is a real number, Aij's are real numbers or elements in the field F. So when you add 0 to any element, you get the same element. So this sum will be A11, A12, up to A1n, A21, A22, up to A2n. And then we have AM1, AM2, up to AMN. So this is member A plus this matrix O, which has all the elements zeros. And this is the matrix A. So we have successfully shown that if we have a matrix with all elements zeros added to any matrix in this set, we get the same matrix. So therefore, identity, additive identity exists on this set F, which is a matrix with all elements zeros of order m by n. Then number 5, additive inverse. Now, additive inverse, we show that if we have a matrix A plus another matrix minus A, then we have the identity matrix. So let A be given by A11, A12 up to A1n, A21, A22 up to A2n, AM1, AM2 up to AMN be an element in this set F of all m by n matrices. Then this implies that negative A will be the matrix, negative A11, negative A12 up to negative A1n, negative A21, negative A22, negative A2n, negative AM1, negative AM2 up to negative AMN. And this is still a matrix in this field, in this set of all m by n matrices. Because negative A is the same as negative 1 times this element, and negative 1 is an element in the field F. So this is what we have. Now, A plus minus A will be A11 plus minus A11, A12 plus minus A12, A1n plus minus A1n, A21 plus minus A21, A22 plus minus A22 all the way A2n plus minus A2n, and then AM1 plus minus AM1, AM2 plus minus AM2, all the way up to AMN plus minus AMN. Aij's and minus Aij's are just elements in the field F, and whenever you add an element to its negative, you get 0. So this will be 0, 0, 0, 0, 0, 0. And then this you get 0, 0, this also 0. So A plus minus A is resulting into a matrix with all the elements zeros. So i.e. A plus minus A is this zero matrix, and therefore additive inverse exists on this set. Now, from the additive inverse, now we go to the closure with respect to scalar multiplication. So closure with respect to scalar multiplication. Now, so let alpha be an element in the field and A be a matrix of order m by n. So alpha times A will be alpha into A11, A12, up to A1n, A21, A22, up to A2n, AM1, AM2, up to AMN. Since scalar multiplication is defined on matrices, then this alpha multiplies every element. So we'll have alpha A11, alpha A12, up to alpha A1n, alpha A21, alpha A22, up to alpha A2n. This one will be alpha AM1, alpha AM2, up to alpha AMN. And you see this resulting matrix is also of order m by n. So it is a matrix in this set F of all by m by n matrices. So therefore, closure with respect to scalar multiplication holds. Holds on this set of all m by n matrices. Number 7, we show distributivity. So if we have alpha in the field, if we have an element alpha in the field and two matrices of order m by n, then alpha into A plus B will be alpha. We have already defined A plus B is A11 plus B11, A12 plus B12, up to A1n plus B1n, A21 plus B21, A22 plus B22, up to A2n plus B2n, and then AM1 plus BM1, AM2 plus bm2, amn plus bmn. And then this scalar multiplies every element. So we'll have alpha a11 plus alpha b11, alpha a12 plus alpha b12, alpha a1n plus alpha b1n, alpha a21 plus alpha b21, alpha a22 plus alpha b22, all the way alpha a2n plus alpha b2n, then alpha am1 plus alpha bm1, alpha am2 plus alpha bm2, alpha amn plus alpha bmn. Now in this sum, we must have added alpha aij's to the matrix alpha bij's. So this is the same thing as saying alpha a11, alpha a12 up to alpha a1n, alpha a21, alpha a22 up to alpha a2n, all the way up to alpha am1, alpha am2, alpha amn, added to alpha a11, alpha b11, alpha b12, alpha b1n, alpha b21, alpha b22, up to alpha b2n, all the way up to alpha bm1, alpha bm2, up to alpha bmn. Now in this one here, remember we have alpha into a plus b. This one means because alpha is on every element, then it must have been alpha times the matrix aij's. So this alpha into a11, a12, up to a1n, a21, a22, up to a2n, and then a2, am1, am2, up to amn, plus also here alpha is common, so we factor it out. So b11, b12, b1n, b21, b22, up to b2n, bm1, bm2, up to bmn. And you see this one is definition of matrix A, and this one is definition of matrix B. So i.e. alpha into A plus B is simply alpha A for this matrix A plus alpha B. So distributivity holds. Therefore, distributivity holds. Last distributivity, number 8. If we have still distributivity, if I have alpha and beta as elements in the field, and then I have a matrix A of order m by n, then alpha plus beta times A is alpha plus beta into a11, a12, up to a1n, a21, a22, up to a2n, am1, am2, up to am, n. And then just multiply by every element. We have alpha plus beta, A11, alpha plus beta, A12, alpha plus beta, A1n, alpha plus beta, A21, alpha plus beta, A22, up to alpha plus beta, A2n, then alpha plus beta, AM1, alpha plus beta, AM2, up to alpha plus beta, AMn. And just multiply, both these are just elements in F. So we'll have alpha A11 plus beta A11, alpha A12 plus beta A12, alpha A1n plus beta A1n, and then alpha A21 plus beta A21, alpha A22 plus beta A22, all the way up to alpha A2n plus beta A2n, all the way up to alpha A21, AM1 plus beta AM1, alpha AM2 plus beta AM2, alpha AMN plus beta AMN. And this is the same thing as having alpha AIJs plus matrix beta AIJ. So this is the same as alpha A11, alpha A12, alpha A1n, alpha A12, A21, alpha A22, up to alpha A2n, alpha AM1, alpha AM2, up to alpha AMN, added to now beta A11, beta A12, up to beta A1n, beta A21, but this is 1, beta A22, up to beta A2n, all the way up to beta AM1, beta AM2, up to beta AMN. And you can always factor out alpha and check that this alpha times matrix A, and this one is beta times matrix A. So alpha plus beta times A gives us this. So which shows that distributivity holds. And it's not hard to also check that number 9, associativity alpha beta. If you multiply by matrix A, you will get alpha into beta A, and 10 also, when you say 1 times matrix A, you also get matrix A. And therefore, you say F m by n is a vector space. So kindly show this, and these are the properties.